Friends, in my last video, I explained unit sample sequence, unit step sequence in detail. I also explained the how to express given signal in terms of linear combination of shifted and weighted unit samples. So every signal x of n we can always express in terms of shifted and weighted combination of unit samples. So x of n, let us consider once again x of n is equal to 4, 6, 9 minus 9, and it is like this. So here we know that samples are sitting at 0, -1 and -2. So corresponding to this minus 9 is sitting at 0, so multiplication by del n. Then 6 is sitting at this one -1, so del of n plus 1, and here 4 is sitting at place -2, del of n plus 2. So this is our representation of signal x of n in terms of weighted and shifted delta function. Unit sample, you can use word delta function. I will be using word delta function for unit sample henceforth. So it is linear combination of weighted and shifted delta function. So if I take x of n is equal to unit step sequence, we know that unit step sequence is a sequence which is existing from 0, having amplitude 1 and having amplitude 1 1 1 1 up to infinity, or we can write like this: it is 1, n is greater than equal to 0, it is 0 otherwise. So it is a causal sequence which is starting from 0 and it is 0 before 0, we can say anything. So it is a causal sequence starting from 0 and ending to infinity, having amplitude 1 1 1. So this is a unit step sequence. If you are trying to write in terms of the sequence form, it is having infinite samples. Each sample has value 1. Okay, so this is unit step sequence. In the same fashion, whatever signal x of n is given, we express that signal in terms of delta function. Now I would like to express same signal in terms of unit step sequence. So we know that that day in the last lecture we have shown delta function can be written as subtraction of un and u of n minus 1. If u of n minus 1 is subtracted from un, we get del n. So if I shift del n by n naught, the equation will be generalized equation, and which will be useful to express x of n in terms of shifted unit step sequence. So let us try to write same equation in terms of unit step sequence. So since we are having definition in terms of definition of delta function in terms of unit step function, so I can replace here 4 del of n plus 2. If I replace n by n plus 2, what we get? U of n plus 2, and minus u of n plus 2 minus 1 means u of n plus 1. So this is for del of n plus 2. Likewise, for next term 6, del of n plus 1 can be written as, put n equal to n plus 1, un plus 1 and un. So un plus 1 minus un. And last term minus 9, del of n we know straight away it is un and u of n minus 1. Use square bracket, okay, for showing discrete time signal. Though I am using many times simple bracket, you use square brackets. So everywhere you use square bracket for discrete time signal, that is standard practice. So here we are trying to express given signal in terms of linear combination of weighted and shifted unit step sequence. So un plus 1 single term, here un plus 1 is there, here un plus 1 is there, we can combine these two. Here un is there, we can combine these two, and u of n minus 1, it is single, so it will remain as it is. So if you are trying to write, it is 4 times u of n plus 2, 4 times u of n plus 2. Here it is 4 times u of n plus 1 in minus sign, and here plus sign, so result is 2 times u of n plus 1. Here it is 6 times minus un, and here minus 9 times u of n, so minus 6 and minus 9, minus 15 u of n, minus 6 un and minus 9, minus 15, and last is minus 9 u of n minus 1. So this is the representation of signal x of n in terms of linear combination of weighted and shifted unit step sequence. So given signal can always be written in terms of delta function or in terms of unit step sequence. So can we write unit step sequence in terms of delta function and its shifted version? So we know that unit step sequence is nothing but having amplitude 1 1 1 from 0 to, here I am writing 0 to infinity. So here it is unit step sequence un. This is the definition of un. So here time index is n. See the first sample at which is present at 0, so which can be written as del n. So the sample which is present at 0, it is a del n. So sample which is present at 1, we can write it is del of n minus 1. Sample present at 2, we can write it is del of n minus 2, because n equal to 2, the value is 1. So here everywhere amplitude is 1. So you can write unit step sequence is nothing but addition of delta function and its shifted version. So it is addition of del n, del of n minus 1, del of n minus 2. So the first amplitude corresponds to del n, second corresponds to del of n minus 1, third corresponding to del of n minus 2, and so on. So up to infinity there are samples, so we can write last term del of n minus infinity. So if you try to write in closed form, it will be del of n minus k, right? Del of n minus k, and k equal to 0. If I say k equal to 0, I get del n. K equal to 1, del of n minus 1. K equal to 2, del of n minus 2. So I can write k equal to 0 to infinity un. Un equal to del of n minus k, where k is varying from 0 to infinity, and summation. Un equal to summation k equal to 0 to infinity del of n minus k. This is also important equation which is required many times while writing un in terms of del n. So un is written in terms of del n, and del n can also be written in terms of un, that is u of n minus 1, which we have seen in the last lecture. So there is a relation between un and del n. So now let us see the one more signal which is also a standard signal in signal processing. That signal is unit ramp signal. Unit ramp signal, the definition is it is n times un, x of n equal to n times un. It starts from 1 and ends at infinity. So unit ramp sequence is proper word, unit ramp sequence. This is third signal coming under the category of standard signals, or we can say they are the basic signals in the signal processing. So it is URN and defined as it is n when n is greater than equal to 0, 0 otherwise. So if n equal to 0, the signal is 0, n equal to 1, signal is 1, n equal to 2, signal is 2. Likewise, as n increases, the amplitude of the signal is also increases. At 0, amplitude is 0, at 1, amplitude is 1, at 2, amplitude is 2, at 3, amplitude is 3, and so on. So URN is equal to, it is defined as n when n is greater than equal to 0, otherwise it is 0. And you can write name of the signal with paint line at the origin. You can write name of the signal URN. Unit ramp sequence. Unit ramp sequence is a sequence which is defined as n times un, which is also a causal sequence because it is 0 before 0. So unit ramp sequence also you can write in terms of delta function as well as in terms of unit step function. I told you that URN, unit ramp sequence, is equal to n times un. So there is a relation between URN and unit step sequence. Unit ramp and unit step sequence, this is the relation. And then we know that un can be written as, so URN and un can be replaced in terms of whatever formula we are having for delta function. Same thing can be used n times summation k equal to 0 to infinity del of n minus k, which is your URN. So let us check for n equal to 0, it is 0, n equal to 1, it is 1, and here k is varying from 0 to infinity, n equal to 1, so 1 into 1. So n equal to 2, it is 2, and this is giving me value 1. So every time this is giving me value 1. So you can take that n inside also if required, because n is not function of k, so only k is changing. So you can write like this, k equal to 0 to infinity, URN, unit ramp sequence. Okay, let us find what will happen if you subtract URN and URN minus 1. So let us do the subtraction of URN and URN minus 1. Okay, let us draw the signal URN plus 1. So signal is URN shifted towards left by 1. So what will happen? We'll see. So instead of it is 0 at 0, it is 1 at 0. It is 1 at 0. Then it is at 1 it is 2, and likewise at 2 it is 3, and it is 4 at 3. So this is your signal URN plus 1. So URN shifted towards left by 1. So let us subtract URN from this. URN, you know that URN starts from 1. So it is 1 at 1, it is 2 at 2, it is 3 at 3, it is 4 at 4. So if you subtract, it is going on. If you subtract these two signals, you will find that there is a difference of 1 everywhere. At 0 it is 1, at 0 it is 0. Right? The signal or whatever sequence I am taking here is URN, and I am trying to subtract this URN from URN plus 1. URN plus 1. And if you see this, everywhere you will find that there is a difference of 1 between two sequences. So what we get then after subtraction, everywhere we get 1 1 1 1 1 1. So we can say that it is 0 to infinity. See here it is 0 to infinity. 0 to infinity, if you see the difference, you will find that, okay, at 0 it is 1, 1 minus, this is 0, 1 minus 0, 1, then 2 minus 1, 1, 3 minus 2, it is 1. So all are 1 1 1. Signal which is having amplitude 1 1 1 from 0 to infinity, we know that that signal is a unit step sequence or unit step signal. So I say that we can say that URN plus 1 minus URN is equal to UN. So we can always write this URN plus 1 minus URN which is equal to UN. UN can be expressed using URN. And we have also seen that UR can also be expressed in terms of UN. We have also seen URN can also be expressed in terms of delta function. All these three signals, they can be expressed in terms of others, and these are the signals they can also be used to express the other signals, general signals. So in discrete time standard signals, we have seen unit sample sequence. We can say this is a delta function which is denoted by del n, and it is 1 for n equal to 0. It is single sample sequence delta function having amplitude 1 at n equal to 0. It is existing at only one point, and if you shift this by n naught, so that amplitude 1 will go at n naught and it is 0 otherwise. So signal is shifted towards right by n naught, and if you shift the signal towards left by n naught, then amplitude will be 1 at n equal to minus n naught, it is 0 otherwise. So this is about delta function. This is original delta function without shift, and this is shifted delta function. Delta function shifted towards right by n naught, then your 1 which was sitting at 0, it will be sitting at n0, where n0 is some positive number, I am assuming. Here n plus n0, the delta function again having value 1, but instead of sitting at 0, it is sitting at minus n naught. So if you know these three things about delta function, you can write every signal using delta function. Okay, this was about the unit sample sequence, which is 1, n equal to 0 and 0 otherwise. And we have seen second signal is unit step sequence, which is un, and having value 1, n is greater than equal to 0, having value 0 otherwise, right? It is having value 1 when n is greater than equal to 0. And we have also shown that delta function can also be obtained or can be written as in terms of unit step sequence minus unit step sequence shifted by 1 towards right. We have also seen that un can also be written in terms of delta function. So del of n minus k equal to 0 to infinity. And the last signal which we have seen is unit ramp sequence, which is, I have told that it is 1, it is n, if n is greater than equal to 1, it is 0 otherwise, means minus infinity to 0, the signal is 0. And we have also shown that this urn can be written as n times un, and also you can we can see that un can be written as in terms of this equation, so that can be placed here. So urn can also be expressed in terms of delta function. So this was about the all standard signals in discrete time case. Now there are similarly there are 3 standard signals in continuous times case, and those standard signals we'll see in the next video. Let us stop here for this discrete time standard signals. Now we'll be going for continuous time standard signals in continuous time case.